Okay, so this video will finish up with our basic data analysis or basic statistics. And just to remind us, we're still in this analysis phase. And if we think back to the last video, remember that statistics used to describe large data sets can say almost whatever we want it to, depending on how we phrase the question, how we analyze the data, and to use to draw conclusions about our data. Okay, but definitely the very important assumptions or things we need to consider is what's the sample size? How much data do we have, right? It's kind of the more data we have, the better conclusion or the better, more accurate statistic we can calculate. And then, of course, today we're going to talk about how our standard deviation affects what we're trying to say the conclusion about, right? So we have a standard deviation, and that really affects our conclusions. And so if we look at measures of variation, these represent how different or spread out or how tight, right, our data is. And so two statistics we use for this are range and standard deviation. Similar, but we're going to find that standard deviation actually is a little bit more robust, and that's commonly what we'll use in industrial applications where we describe the variation in our data. So if we talk about range, of course we can think of range as just the max value minus the min, right? It's just how spread out the lowest to the highest is. So we have a set of data. Here are our K different salaries. And so what's our range? So we can just take these, order them smallest to largest, and then just calculate the maximum value minus the min value, and we have a range of $10,000. K being kilo, 1,000, right? So this is our back to our metric prefix. So $10,000. So that's range, easy to calculate, shows just the largest to the smallest. Standard deviation is a little more intricate, and basically what we're doing here when we calculate standard deviation, we're measuring again how spread out the data is from the mean. So we have the mean, x bar, and we're saying how far away from the mean is the data, is our data set. And so actually, if you notice, this part of the equation, okay, the top part of that fraction is very similar to how we calculate error. If you recall, we have error at n bar minus n. So n bar minus n. And so that was how we calculate how far off we are from our target. How far off is our measured value from our target. So that's a similar concept of what we're doing here. We're saying each individual measurement, how far off are we from the average? Okay. And of course, we're going to do some other things. We're going to square it. We're going to divide by 1 minus, or our sample size minus 1. Okay. But this is going to give us a statistic that shows us how spread out our data is. And of course, we have a large standard deviation, widespread data. Small standard deviation, narrow spread data. Okay, so we can look at this graphically here. We have three different data sets. The first one has a 0 standard deviation. There's no variation. All of our data are clumped at 5. Okay. Then we have a 1.2 standard deviation. A little more spread out, right? A little more spread in our data, kind of basically from maybe 2.5 up to 7.5. Then in the standard deviation of 3, we have a much further spread in comparison to these other two. So when you talk about standard deviation, okay, we got to remember that it's a comparison. We use the value to compare it to one or more data sets. So one single standard deviation value on its own is meaningless until we compare it to the standard deviation of another data set or some benchmark standard deviation, okay? Which we're going to find a lot of statistics, they're used to compare things. So if there's nothing to compare it to, it doesn't really mean a lot. But once we start comparing, right, our statistics, then we can actually start interpreting some meaning and drawing some conclusions, okay? So of course from this graphical, the data set on the left here is the most tightly grouped versus the data set on the right is the most spread apart. So we can take our class age data set from previous video, and we can calculate our ranges and our standard deviation. And of course, we have a range of 45 and a standard deviation of 9.81. Okay, and again, this number here and this range of 45 may not be very meaningful to us just by themselves until we actually compare it to something. And so if we look at our frequency distribution of our data again, of course we had our range at 45, our standard deviation at 9.81. We can graphically, of course, we can see that this standard deviation and this range is going to be very affected by this outlier, right? Because the standard deviation and range that tells us how spread out it is, right? So if we have this really far outlier, of course, that's going to influence those calculations. So if we remove the value of 65, we drop down to a range of 4 and a standard deviation of 1.43. Okay, so I'm not saying we're going to remove the outliers. We talked about we're going to leave outliers in there for this class. But just the comparison of how much they're affected by outliers. So they're extremely affected. Okay, I mean we would drop down almost close to 9 times less than the standard deviation when we just remove that outlier. And so we can look at standard deviation and range in this table here as very much affected by outliers, so extremely affected by outliers. Okay, the standard deviation accounts for all the data in the data set, whereas the range does not. It only accounts for the highest and lowest. Okay, and of course the standard deviation is related to the mean. It actually has the mean as part of its calculation, whereas range is not. And this is a big one. Standard deviation we should be using when we talk about normally distributed data. Okay, so the data that has a nice bell-shaped, almost something that we could have a mirror image of, side to side, right to left. Okay, so again, standard deviation is more descriptive than a range. It actually gives a better description because it takes all the data into account, and it shows the accuracy or inaccuracy of our data, right? So it gets at kind of the error of our data. And then of course the range clearly describes the width of the data, but it's less descriptive because it doesn't account for all of the data in the data set. It only accounts for the highest and lowest. So before we go over to Excel, there's just one more concept that is actually very important when we start talking about how we use standard deviation and how it relates to normally distributed data. Statistically, it's been proven that based on if we have a normally distributed data set and we calculate our standard deviation and our mean, so we have our mean calculated and we have standard deviation calculated, that if we take our mean plus 1 standard deviation and our mean minus 1 standard deviation, between those 2 points, there is 68% of our data between those 2 points. Okay? If we say, change colors here, if we say plus and minus 2 standard deviations, okay, so we have the mean plus 2 standard deviations, the mean minus 2 standard deviations, we're now at 95% of our data, roughly, will be between plus or minus 2 standard deviations from the mean. Okay, so we'll get 95% of our data in between these two values. Okay, and of course it follows then that 99% of our data will be between -3 standard deviations and +3 standard deviations of our data. So what this tells us is if we have a normally distributed data set and we calculate our mean and we calculate our standard deviation, we can determine where, in 68, 95, 99% of our data will fall into what range. Okay, and where this comes important is in a lot of quality work, okay, in manufacturing and agricultural scenarios where we have collected data and we want to see how much of our data is between 95% of our average that we're shooting for. So maybe in this conversation we talk about average as our target, right? We're trying to have an average of 23. Okay, and say this is a paint spray application where we're having a flow rate of a paint sprayer as the part comes by on the conveyor. And of course, the more the flow rate, the thicker the paint. Okay, the slower the flow rate, the thinner the paint. Okay, and if on average, we take say 100 samples of flow rate, and on average we have a flow rate of 23. We can calculate standard deviations, right? Maybe at -1 standard deviation, +1 standard deviation, and we would know from the previous slide in this concept of standard deviation and normally distributed data that there's actually between 16 and 30 is 68% of the time we had a flow rate of between 16 and 30. Okay, so 68% of the time, that's where our flow rate went between. If we look at, change the color here, if we look at, say, 95% of the time, okay, so now we want to say 95% of the time, what's our flow rate based on our data? And that was our flow rate was between 9 and 37. Okay, so plus and minus 2 standard deviations from our mean. Okay, so now you can start seeing that we know our average or our mean, we've calculated standard deviation, we can now start interpreting how much of the time or how much of our data set based on percentages were between what range of values. And where this really comes into play is, let's say our customer tells us that we want, a thickness of, X centimeters, okay? And that thickness, to get that thickness, plus or minus some tolerance, right? To get that thickness, we want 23, a flow rate of 23 to get that target thickness. Well, then they say there's a tolerance, right? Because we don't live in a perfect world. The real environment of the spraying operation is going to have some error in it, and so we're going to allow you to go, plus such a thickness, minus such a thickness. Okay, and so what that means for us as a manufacturer is, okay, if I have a target of 23, but I'm allowed to go down to 9 and up to 37 on my flow rate, and that corresponds to different thicknesses of that material. What this tells me is, based on this data set I've collected, if I produce 100 parts that are sprayed, 95 of them will be within tolerance. 5 of them will be out of tolerance. I won't be able to give that to the customer and have them accept that as within their tolerance. Okay, this is where we're starting to use statistics to show us and model for us and calculate how many parts that we produce are within tolerance versus how many parts are out of tolerance, okay, and either need to be reworked or thrown away, okay. And so a lot of times companies don't look at the 95% range, they're looking at the 99% range, okay, and above. Okay, look right here, the 99% range and above. And actually they're looking at 99.997 range, okay? Because when you make hundreds of thousands and millions of parts a day, even small percentages can account for a lot of actual parts that are out of spec. So this concept of the standard deviation of a normally distributed data set is really, really important when you talk about manufacturing and production and how you can track that and calculate production rates. So we're going to turn now to the statistics in Excel, and we're going to just go through again briefly these functions in Excel. So we'll flip over to that. And again, I have this same file here, example for PowerPoints 8 and 9. And just like we did before, there's no specific range calculation, but we can do a min and a max function and then use that to get our min and our ranges. So in Excel, and I like to use this formula builder or insert function. So I can type in min, hit go, and so I'll double click this and get my minimum and maximum. And so if I want to, I know that the first value is B4. okay? And of course, the last value is B504, okay? So I can just go ahead and type those in. I don't need to scroll down. If I know the cells that they go to, I can just type them there. And that, of course, is my data set. And so, actually it went to 503. So I can just do that. And then, of course, my max equals max, if you had that assumption that that was correct, for colon B503. Okay, so there's my min and my max. And I can do a range. I can say my range then equals my max, that cell, minus my min, that cell. And I can build that there just like that so that this equation is dynamic, so that whatever is in this cell will be calculated for my ranges here. So if I change this cell to say 10 and 1, of course I've dynamically recalculated my range. Okay, I'll go back to that. Another way we can do this, if you look over here, we can actually put these functions together in all at the same time. So we can actually say equals max B4 colon B503 minus min. And so we can actually build this equation on the fly or all together and calculate that just all in one line or in one cell. And that's, at this point, is a preference for you. But understand that we can combine functions together to calculate different values. And so we've calculated our range. Now we can calculate our standard deviation. And again, I'll go here and standard deviation. And I forget these things too after a while, unless you use them enough. You're going to forget things unless you're using them, multiple times in a week. But this is important here. Standard deviation, there's a couple different things here. When in this class, we're going to use standard deviation.s. So stdev.s. Estimate standard deviation based on a sample. Okay, which is what we're going to talk about. We're going to collect samples. Okay. .p is a population. If we had the entire population, which that hardly ever happens. Okay, but today we're going through the sample. In this class, we're going through the sample. So .s. We hit OK, and I think we remember that it's B4 semicolon B503, and we can just type that in. And so our standard deviation is 0.005155. Okay, and again, just like we did previous, we can copy these over. So what if we wanted to find, based on our standard deviation and our mean, where 95% of the data for black fell within? So we could say equals, and I'm going to put this in parentheses, mean minus parenthesis this times 2, right? So 2 standard deviations will do the 95% interval. Okay, so from that number, and then of course mean plus this times 2, that number. Okay, so between these two numbers, mean minus 2 standard deviations and mean plus 2 standard deviations, 95% of our data will lie between those two values. Of course, we can calculate that over. Okay, and this may be helpful. We can reduce the decimal values here to kind of get a nicer number here. This might help us to kind of just get an idea of 95% of the time where our data lies. And of course, this is the average, and this shows the spread. So if we look and we compare these, okay, we can see that black had the least variation, right, the lowest variation, whereas the yellow had the highest variation. Okay, and you see this trend here. The black values were the lowest voltage values on average, with the yellows being the higher. And so the variation, of course, followed that. Tightly grouped data at low voltage values, more widely grouped data at higher voltage values. Okay, so that's some interpretation now we can draw from these data sets. And it looks like that's a kind of a trend as the average increases, our variation increases, and that may or may not be common, right, between data sets, but of course as well it's common. It's what's happened here. And we had previously graphed the the histograms of these, and so we could do that again, and we could compare, right, graphically the spread of our data graphically. We won't do that now, but you could do that. You could plot your histograms of each and see graphically the differences in the spreads, and be careful to look at the bottom x-axis, and that might not be on the same range. Okay, so it might look visually equal, but it's actually numerically different ranges. Okay, so that's variation in statistics, so range and standard deviation, and those are very helpful, especially when you combine standard deviation with mean to help us find 95% intervals of our data, or 99% intervals of our data. And one last thing, if we hit Control tilde, this will show us the functions that are being calculated in each cell. And so this will show us what is being calculated in each of these cells. So if we're have a data set spreadsheet and we're not sure what the actual functions are, or we want to see what the functions are, we can just hit Control tilde. It'll show us that, and we can hit Control tilde to go back. We can always double click on the cell and it will show us where it's looking. It'll highlight the cells or the range of cells that it's using in the calculation. We can also look at, when we double click here, we can click on the actual function and we can get a little description of what that function does and how to type that in and how to work with that function. And it gives us a little example here of how to do that. And so that's the case for all of these functions. And hit escape. Escape's your best friend to get out of that. That's the same for all of these functions. It'll give you a little dial-up window of kind of explaining what that function does and how it operates. Okay, with that, I'll see you in class.